Right then, so welcome to Calculus 2, Math 142. I am Mark Sullivan, and as you can probably tell from contextual evidence, I'm the instructor for this course. Pretty much everything you need to know is on the syllabus, which, normally I would say that you should read it, of course, but now I would say especially that you should read it, because there are some details in there concerning the fact that this is an online course that you really need to be aware of. So please do take a look at that. And I would recommend bookmarking or favoriting or whatever the course webpage, because everything's going to be there. UB Learns exists as well, but I'm probably going to put most things on the course website, and then UB Learns is just like an afterthought. So anyway, let's get right into it, shall we? So, Calculus 2 is organized into 4 parts corresponding to 4 goals. The first goal is to provide strategies for solving integrals. The second part is to introduce the theory of infinite series. The third part is to extend calculus to parametric and polar curves. And the final part, which I'm not sure if we'll get to this semester just because it's unclear how things will go, pandemic and everything, to apply integration to problems in geometry. Okay, so that's our goal right now. These first 3 goals for sure we will get to, and then the 4th goal, if we manage to have some time, we will get to that as well. Right then, so in Calculus 1, you explain the theory of the solutions of the tangent line problem and the area problem. These were related by the fundamental theorem of calculus. Fundamental theorem of calculus just states this. So this is the fundamental theorem of calculus. If f is continuous on the closed interval from a to b, where a and b are some real numbers, then, well, it had 2 parts. The first part was that the derivative of the integral from any constant up to x of f of t dt was always just equal to f of x. The second part was that if f is an antiderivative of f, so if capital F is an antiderivative of f, then if you want to integrate f from a to b, this will always end up being capital F at b minus capital F at a. Okay? And hopefully this looks familiar from Calculus 1. So this tells us that integrals, definite integrals in particular, can be solved using antiderivatives. Great. The problem is that finding the antiderivative is much harder than finding the derivative. And so, therefore, the first part of our class, Calculus 2, will focus on strategies for finding antiderivatives. All right? But first, let's take a minute to just review what we know from Calculus 1, shall we? So, of course, there's the fundamental theorem of calculus, and that explains the importance of having the antiderivative. But how do you compute them? Well, let k be a real valued constant. Okay? So if k is a real valued constant, then all of the following formulas will apply. First of all, the indefinite integral of 1 dx, well, this better just be x plus c, right? Because, of course, any function that has a derivative being 1 has to be x, or maybe x plus a constant. Okay? Now, provided that k is not equal to -1, the integral, indefinite integral of x to the k dx, this should always be x to the k plus 1 divided by k plus 1 plus c. Right, so you just add 1 to the exponent and then divide by the new exponent. And this is pretty much the backwards of the power rule. The only reason this wouldn't work is if k were -1, because if k were -1, then k plus 1 wouldn't make much sense to put in the denominator, because it'd just be 0, right? So then this begs the question, what happens if k is -1? Well, the answer to that is given by this one. The antiderivative of 1 over x is just the natural log of the absolute value of x plus c. The antiderivative of e to the kx dx, this is just e to the kx over k plus c. And I guess I should say here, if k is not 0. Obviously, if k is 0, then first of all, this is just going to be 1, so you probably wouldn't bother thinking of this as an exponential in the first place, but more importantly, it wouldn't make sense to put 0 in the denominator again. Okay. Then there's a few trigonometric functions that we know. We know that the antiderivative of cosine x, this is just sine x plus c. We also know that the indefinite integral of sine x, this is negative cosine x plus c. There's a few more that we know because, for example, the antiderivative of secant squared x, this is tangent x plus c. The antiderivative of secant x tangent x, well, this has got to be secant x plus c. The antiderivative of cosecant x cotangent x, dx. this has got to be negative cosecant x plus c. And then the antiderivative of cosecant squared x this is just going to be negative cotangent x plus c. All right? And there's three more coming from the derivatives of the arc trigonometric functions. So the antiderivative of 1 over x squared plus 1 dx, that is going to end up being arctangent x plus c. Indefinite integral of 1 over square root of 1 minus x squared dx. That is arcsine x plus c. And then finally, indefinite integral of 1 over x times the square root of x squared minus 1 dx. This becomes arcsecant x plus c. Okay? And hopefully all of those expressions look familiar, or at least can be deduced from what you learned in Calculus 1. In Calculus 1, you probably learned all of these statements backwards. You probably said, like, the derivative of secant x was secant x tangent x. And, you know, that's saying the same thing, right? Okay. There's a few other rules for integrals that we know already from Calculus 1. One of them is that, again, if k is a real valued constant, then if you have the integral of k times any function whatsoever, dx, then you can just pull the constant out of the integral. So this will just become k times the integral of f of x dx. Right? Also, if you have the integral of f of x plus g of x, well, that's just going to be the sum of the integrals of f and g, right? Okay. And these two properties are called the linearity of the antiderivative operator. The derivative also has these properties, right? If you have the derivative of a constant times a function, you can pull the constant out of the derivative. And if you have the derivative of a sum of two functions, that's just the sum of the derivatives, right? For definite integrals, hopefully, in Calculus 1, we also learned that if you have the integral from a to b of f of x dx, where a and b are some real constants, then you can switch the bounds as long as you're willing to multiply everything by -1. So this becomes negative integral from b to a of f of x dx. Okay? Also, if a is less than or equal to t, which is less than or equal to b, so in other words, t is a real value between a and b, then if you want to find the integral from a to b of f of x, you can write that as the integral from a to t of f of x dx plus the integral from t to b of f of x dx. Okay? And so that's pretty much the basic rules of integrals, right? That's our base, sort of. Now then, The last thing that we should have learned in Calculus 1, I'm not saying that as like blaming you for not learning it, it's just, pandemic happening and sometimes classes don't get to it. The last thing we should have learned in Calculus 1 is a topic called substitution, which is a strategy for finding the antiderivative of certain functions. So, seeing as how, once again, as I said, some classes don't get to it, we will review this, and that will be the topic of this first lecture, substitution. Okay? So, in the book, this is section 5.5, called the substitution rule. Okay? Right then, so here's how it goes. Let's look at an example. Suppose we're asked to evaluate the integral of x over x squared plus 1 dx. Okay? Do you know how we might do that? Well, we can't really do it just from the things that I wrote on the board before, because it'd be really hard to think of a function whose derivative is x over x squared plus 1, right? I mean, maybe that's the result of some kind of quotient rule, but you can't do that backwards. So, the way that you should take care of this is with what we call substitution. Here's how it works. We're just going to take a piece of this integrand. By the way, the thing between the integral sign and the dx is called the integrand. It's the function you're integrating. We'll take a piece of this integrand and call it u. In this case, I want to say u is x squared plus 1. Okay? Now, if you do that, well, there are some consequences to that. First of all, of course, if you take the derivative with respect to x, then what you'll get is 2x, right? That's just the power rule from Calculus 1, and of course the derivative of a constant is 0. Now, we are going to write this in a very particular way. Du dx equals 2x. We'll write it in a slightly different way. We'll write it as du equals 2x dx. And at first that looks pretty baffling, right? Because, the derivative is not a ratio. This is not a fraction. This is not du divided by dx. It's just an operator. So how can you multiply dx by both sides? And in any case, what the hell is a dx just by itself? Or a du? Well, don't think of these as separate objects in and of themselves. Just think of this as a notation for this statement. That's all it means. Okay? This is just saying that the derivative of our u is 2x. Right? Now then, if we know that u is x squared plus 1, we're just calling x squared plus 1 u, then du will be 2x dx. Now, if you look at this integral for a second, you notice that x dx does appear in this numerator. Well, and furthermore, if you take this right here, and you say, all right, well, I'm going to divide both sides by 2, then what you'll get is 1/2 du equals x dx, which is exactly what we have here, right? So, now this integral can be rewritten as the integral of 1/2 over u du. Okay, and by the way, this 1/2 is a fraction in and of itself. Whoa, sorry. This 1/2 is a fraction in and of itself. It's a compound fraction now. But that's fine because, of course, 1/2 is a constant, right? So that means, again, we can just pull it out of the integral by the linearity of the integral. So this now becomes 1/2 integral of 1 over u du. Okay? Now this is a lot easier to handle. This is a lot easier to handle. We happen to know what function has a derivative of 1 over u. It would be ln the absolute value of u, right? And that's what this is, right? So this just becomes 1/2 ln absolute value of u plus c. Now, there is something unsatisfying about this answer, and it's that we had the original function in terms of x, so we'd like its antiderivative, or its indefinite integral, to be in terms of x as well. Well, if you want to do that, that's not hard. All you need to do is say, well, u is just a name for x squared plus 1. Therefore, what we're looking at here is, in fact, 1/2 ln absolute value of x squared plus 1 plus c. And that is our indefinite integral. Okay? So this right here is our final answer to that indefinite integral. By the way, I just want to point out, there's nothing wrong with keeping these absolute value signs here. Like, it is supposed to be that. It's just x squared plus 1 is always positive. You can't make x squared plus 1 negative if x is a real number. So if you desire, you can just write this as ln parentheses x squared plus 1. That's the same thing. Okay? Anyway, so this is the idea. U substitution is just taking a piece of the integrand and naming it u, and then seeing how the integral can be rewritten in terms of that substitution. Okay? So, of course, let's do some more examples. So, next example. This one is asking us to evaluate a definite integral. This definite integral is from 0 to pi over 2, and the integrand is e to the sine x cosine x dx. And once again, you look at this and you're like, what function has a derivative of e to the x times sine, e to the cosine x, e to the sine x cosine x. You know, what function has this as a derivative? That'd be really hard to figure out just on its own, right? So, if you want to figure this out, again, we can do u substitution. The way we do this is we'll select some piece of this integrand and then write the whole integral in terms of that. Now, last time we selected the integrand to be x squared plus 1. This time we're going to select it to be sine x. Okay? So u will equal sine x. In that case, du is going to be cosine x dx. Right? Because again, this is just notation for saying that the derivative of u is cosine x. So, when you do this, let's see here, we have u right here, and we have du right here. So this just becomes the integral of e to the u du. All right? Now, there's one little problem with this, and that is that this is a definite integral. So this should also be a definite integral, right? And it is. But the bounds will no longer be the same. You see, the bounds before were in terms of x. This is saying x equals 0 to x equals pi over 2. We need to somehow rephrase that to being in terms of u. We need to say u equals something to u equals something else. So, here's how we do it. You see, when x equals 0, well, let's see, when x equals 0, that's the same thing as u equals the sine of 0 So u equals the sine of 0, and by the way, the sine of 0 is just 0. So when x equals 0, u equals 0, and that means that this lower bound here is going to be 0. Now, when x equals pi over 2, the upper bound, when x equals pi over 2, u is going to be the sine of pi over 2, which is 1. So u now becomes 1. And that means that this upper bound changes to be 1. So this is now the integral from 0 to 1 of e to the u du. Okay? So then, as you know, the derivative of e to the u is just e to the u. And similarly, the antiderivative of e to the u is also e to the u. So this is going to be e to the u evaluated from 0 up to 1. So then, we get e to the 1 minus e to the 0. And of course, e to the 1 is just e, and e to the 0 is just 1. So this becomes the number e minus 1. Okay? And so that's another example of how u substitution can be very useful. Okay? Now, you might have noticed here, I just kind of selected u to be these things in both of these integrals. And that is the hard part. When you're doing an integral, you don't know ahead of time what u should be. Here, it happened to be a good choice to make u sine x. But if we had chosen poorly, if we had said u equals something like cosine x dx, well, when you do that, you get that du becomes negative sine x dx, and then there's no real way to make the rest of this work out so that dx and negative sine x are together. So basically, when you're doing a u substitution, you have to make a very particular choice about what u should be. Otherwise, it's just not going to help you. And that involves some trial and error, some practice, to see what these things have to be in order to make the integral work out well. So let's do another example. Right, so this one is going to be the integral from 1/2 up to 1, so a definite integral, of e raised to the 1 over x divided by x squared dx. Okay? And once again, you look at this and you're like, what function has a derivative of that? And yeah, that would be a very hard problem. So, in order to do this, let's do a u substitution. Now, there is no rule that I can communicate to you about how you should choose what u will be in a u substitution. It just takes practice to get used to how these things work out. So, let's first make a bad choice for u and just see how that doesn't help us. So I'm going to make the choice u equals x squared. This is a bad choice, by the way. This is not how the problem is going to work out. Okay, u equals x squared. In that case, du equals 2x dx. Right then, this x, where's it going to go? I mean, I guess there's an x here, but there's a 1 over it, and it's also an exponent. So how could you possibly put this x into this integral in a way that would make sense? The bottom is u, and that's fine, but this x needs to go somewhere as well. So when you get to this point, you say, all right, we're stuck. And so you try something else. So math goes sometimes. You just have to try something. If it doesn't work out, try something else. So the wiser choice for u would be to make it 1 over x. Now then, if u is 1 over x, well, we want to take the derivative of that, and the derivative turns out to be negative 1 over x squared. You can figure that out by saying u is x to the negative 1 and then doing the power rule on that. So you get negative x to the negative 2, which is the same as negative 1 over x squared. Okay. Right then. So this now becomes the integral of, let's see, this is just going to be e to the u now. And then we have an x squared in the denominator, but this du can take it. So we now have negative du. And that's it. Right? Because, of course, there's this negative sign here, so we need to cancel it with another negative sign. But du is just negative 1 over x squared dx, which is exactly what we have here. Okay? So then, yes, what we're looking at, and by the way, we can take the negative sign outside because it's a constant, is negative e to the u du. Now then, as before, whenever you have a definite integral, you need to change the bounds. So, we're going to change the bounds from 1/2 to 1 to something else. So, when x equals 1/2, u equals 1 over 1/2. 1 over 1/2 is 2. When x equals 1, u equals 1 over 1. 1 over 1 is 1. All right? So now these bounds change from 1/2 to 1 into 2 to 1. So this is now negative the integral from 2 to 1 of e to the u du. Now, there's nothing wrong with this. It's not a problem to have the lower bound be larger than the upper bound. But, I don't know, kind of looks ugly, don't you think? So, we can do that thing where we switch the bounds and multiply everything by negative 1. We can write this as the integral from 1 to 2 of e to the u du. All right? Now, of course, as we said before, the antiderivative of e to the u is just e to the u. So this becomes e to the u evaluated from 1 to 2. All right, well, e to the 2 is whatever e squared is, and e to the 1 is just e. So this just becomes e squared minus e. And that is our value for that definite integral. All right? Side note, this isn't my first time teaching a lecture, but it is my first time teaching a lecture electronically. So it's just kind of weird to me that I don't pause to ask questions, because obviously you can't answer me right now. But yeah, anyway. Speaking of which, because this is my first time doing something quite like this, of course, I'm open to criticism. If you have any suggestions for how we can make this class better, please let me know. Right, so back to math. So let's do another example. Let's say now we're asked to do the indefinite integral of ln x divided by x dx. All right. So here's how we sort of evaluate that u substitution should be done in the first place. You do u substitution when you have an integrand where a piece of that integrand can be called u, and then the derivative of that piece is also present in the integrand. Okay? So when I look at this, what I think to myself is I say, well, ln x, all right, if I were to call that u, hypothetically, then du would be 1 over x dx. 1 over x dx happens to appear here. So, perhaps, well, I'm saying perhaps, but I know it's going to happen. Perhaps it would be useful to say u equals ln x. Let's see what happens. So, u, let's say that's ln x. In that case, du is 1 over x dx. And then everything we need is right here. This now just becomes the integral of u du. Right? And because we don't have a definite integral, there's no bounds to change. So we don't have to worry about that part right now. Anyway, now we have the antiderivative of u du. Well, u is also the same as u to the first power, right? So we can do the power rule on this. We can say, all right, add 1 to the exponent, divide by the new exponent. You add 1 to 1, you get 2, and then you divide by 2. So you get 1/2 u squared plus c. Now, at this point, once again, there's something unsatisfying about this answer because it's not in terms of x. So what we need to do is convert it back to terms of x by just saying, all right, u is just a name for ln x. So what we're actually looking at here is 1/2 ln x squared plus c. And that is our indefinite integral. So just to recap what you've probably noticed already, when you have a definite integral, you need to change the bounds when you do a u substitution. When you have an indefinite integral, you need to translate your answer back into terms of x. Okay? Now, some of you might have experience translating your answer back into terms of x even when you're doing a definite integral. And that works as long as you use the original bounds for x. Personally, I don't prefer that method, but it's not invalid. It does work. I prefer to just change the bounds because once you do that, you can just do the integral. There's no need to even think about u anymore in terms of its relationship with x. But either way works. Okay, and let's do one more example. This one is the indefinite integral of cotangent x dx. Okay, and you look at this for a second and you're like, well, what? So first of all, it's not negative cosecant squared x. That's the derivative. We're trying to take the antiderivative, right? So that's not it. You look at this, though, and you're like, all right, well, if you try to do a u substitution on this, maybe you'd say, like, u equals cotangent x. But then du would end up being negative cosecant squared dx, and there's no place to put that. It's true. That would be a problem. And so, therefore, I would not recommend saying u equals cotangent x. But I would recommend something else. You see, often a good strategy when you're faced with an integral involving trigonometric functions is to break it down in terms of sines and cosines. That's not always helpful, but sometimes it is. So this one right here, cotangent x, by definition, cotangent just means cosine over sine. So what we're looking at here is, in fact, the indefinite integral of cosine x divided by sine x dx. Now that looks like something you could work with, right, in terms of u substitution. Because if you say u equals sine x, now du becomes cosine x dx. And so that's exactly what we're working with here. So if we say u equals sine x, then du is forced to be cosine x dx. In which case, what we have here is the indefinite integral of 1 over u du. And then with that, of course, the antiderivative of 1 over u is ln absolute value of u. So this becomes natural log absolute value of u plus c. And as usual, when you have an indefinite integral and you did a u substitution, you end up with an answer in terms of u, but that's not satisfying because we want one in terms of x. So we just have to say u is sine x. So what we're actually looking at here is natural log of the absolute value of sine x plus c. And that is our indefinite integral. All right? Now then, there's just one more thing we should say about u substitution. It doesn't always work. So, for example, let's see here. Does u substitution did I spell that correctly? Substitution. Yes. Okay. Does u substitution always work? Well, let's take a look. Let's say we have the integral of x times the sine of x. Okay. Well, let's see here. First of all, it is never a good idea to set u equals x in a u substitution. It's not harmful. It's just that it's never helpful, because if you do that, then you get back the exact same integral you had before, except now all the x's are replaced with u's. So that doesn't help. So u equals x, let's not do that. U equals sine x, well, if you do that, then du becomes cosine x dx, and there's no place to put that cosine now. What if you say u equals x sine x? Well, if you do that, then you have to do the product rule to find the derivative, in which case you'll get x cosine x plus sine x as du, and there's definitely no place to put that, right? So, no matter what you choose for u here, you're not going to make any progress with this, in terms of u substitution. How about x natural log of x? Same problem, right? How about x squared e to the x? How about natural log of x? How about e to the x cosine x? None of these can be done through u substitution, right? So, we need something else. And that will be the topic of our next lecture. Well, actually, it'll be the topic of, I guess, this topic in the class. But in any case, yes, we're going to need something else, because u substitution obviously is not perfect. It cannot do everything for us. That's going to be a common theme in calculus 2. There's no single strategy that will work for every integral. So you're going to have to sometimes learn a bunch of different strategies and then say, let's see, is this going to work? Is this going to work? Is this going to work? It's not easy. Well, as I said, taking the antiderivative is much harder than finding the derivative. Right then. So that's it for today, today's lecture. Homework is posted on the website. As the syllabus says, there are only 5 problems per section, so hopefully it won't be too intimidating, just to give you some practice. And there will be a quiz on this lecture and the next lecture on Tuesday of next week. So that's it for today. I don't know how to conclude this. Whatever. Okay. Bye.